Hello and welcome to this Elector webinar brought to you today by NXP. Today's topic is From Lab to Road, bringing EIS accuracy into everyday battery management control. And there's no better expert to tell us about it than Dr. Wenzel Prochazka. Wenzel, how are you doing?
Very good, and you?
I'm doing excellent, thank you. Looking forward to this one. Just to tell the audience about you, with more than 15 years of background in EV battery and powertrain development activities, Wenzel joined NXP in 2023 to manage the electrification system products elaboration. And today he manages the process of NXP building systems for HV batteries and linking to customers, as NXP supports customers with a larger part of the value share in innovative system solutions in processing and analog. So we've got an audience around the world. As always, we've got Frank de Hat from Velen, Belgium. We've got Scotland, Colorado. That's early in Colorado. So this must be quite interesting. The Netherlands. Hello from Nokia, interestingly enough. So we've got people from around the world. Wenzel will do his presentation. That will take about 47 minutes. And then after his webinar, we're open for questions. So please drop your questions, your Q&A, in the comments, and we will take them after the webinar. So I think with all of that, thank you to everyone for joining us. Thank you, Wenzel, for joining us. I think we can hand over to you now for the presentation.
Welcome also from our side, Philippe and mine, and we will jump right into the webinar today. So what are we doing here? We are trying to design chipsets for BMS systems that will support the surging electricity demand on the mobility side, on the grid side, and also on the industrial side. So you see there from the bikes over PV, over grid connected ESS systems, all of these devices do need energy storage, and this energy storage should be as safe as possible. And this is where our EIS system, so Electrochemical Impedance Spectroscopy system, comes in. It is a chipset, and this chipset is supposed to go into the battery management system, or this chipset underpins a battery management system on the hardware side. So these battery management systems, they really need to be efficient in order to be sustainable, because if such a battery is on 24/7 for a decade or even longer, then every watt really counts that you put in there. So you don't want to waste energy. You want to be safe, you want to be secure, especially with the upcoming threats in the security. In the cybersecurity space, you want to have a BMS system that really works out with a secure endpoint, with a safety. So this is not part of today's talk, but it will be on some of the upcoming BMS talks that we will have from NXP side. So if you want to listen in there, stay tuned on that. And then the points of time to market and cost. We really need to support as many people as possible in getting their BMS systems to the market at an acceptable cost and the acceptable scalability in order to bring those systems really in a large scale into the market. And one of the main parts of where this time to market and cost really starts to hamper is in the complexity of getting such a system safe, preventing thermal runaway, getting fast charging really implemented correctly, that you also have controls during that 10 to 15 minutes, and you don't just watch how the battery is filling up and you're trying to cope with it, but you're not there. So how do we do that, and how do we support that? We just introduced about 2 weeks ago our BMS chipset with a built-in electrochemical impedance spectroscopy feature that is using a precise hardware-based synchronization for all the battery cells measurements within the single high-voltage battery pack. What does that mean? That means that we have a nanosecond level synchronization of all the cell voltage measurements and the pack current measurement. So we're using an pack level excitation as opposed to modular cell level excitations on other systems. We're using one single excitation wave that travels through the whole pack, through all of the cells, and we're measuring the current on the pack level. So we're including all of the overlay and bias currents in that current measurement in order to really measure the response of the cell to all of the excitation that is there. And we measure all of the cells at the same time, which means that you get a really comparable cell-to-cell measurement in which you can, hopefully, you won't have that issue, but in case you should, hopefully find any kind of outlier cell that is starting to go in any kind bad. In order to support timing and cost competitiveness, we made this EIS chipset pin-to-pin compatible with our standard chipset. So I will introduce that numbering scheme which shows the pin-to-pin compatibility to you in a later slide. And we're reusing the whole existing system architecture on a safety side, on the software side, on all of these features. With the excitation on the pack level, we enable you actually to be very power efficient. So if you want to do an excitation and you want to not lose energy, then you need to store the energy of the excitation wave in a secondary energy storage. So you can either do that in the DC link capacities of the other high voltage parts, or you use the low voltage battery for that, or you use a half pack excitation. So there's multiple versions that you can use, and we're supporting for example, now with our parts, the DC link as the secondary energy storage. So you only have transmission losses and you do not lose the energy of the measurement excitation. Yeah. And we are targeting, finally, accuracy levels in line with commercial lab equipment, which means that you should be there in the micro-ohm level of repeatability of the measurement, depending on the conditions of the battery cell that it is currently in. I told you that we're targeting pin-to-pin compatibility. So you have here the numbers, the part numbers. With the BMA 7418 being the cell measurement device. So the 74 means 7 series, the 4 means EIS capable, and 18 means 18 cells. It is completely pin-to-pin compatible with the 7118, which is the standard device without EIS. Same goes here on the BMA 8420, which is the BJB or battery junction box device, which does the current measurement and it does the control for the pre-charge device that will do the excitation via storage of the energy in the DC link capacities. And then finally, you have the centerpiece, the heart of the system, which is the gateway. The SPI or CAN to transport layer protocol to TPL protocol. And this is the BMA 6402 with the standard part without EIS being the 6002. So we designed the system to really give you an advantage in adding something to the BMS system, in not having too much effort to add this to the BMS system. And what does the EIS really do for a BMS? The EIS is a way of supporting a BMS control algorithm in very dynamic situations. So you can get faster to a resistance measurement. You can get faster to a nonlinear current response resistance measurement in fast charging, for example. So in the end of the day, by giving you a resistance measurement, a repeatable resistance measurement within seconds instead of within minutes or even longer, if you're trying to figure out what the exact time synchronization of the measurement points and the current, let's say, pulse segments are, we can give you something that is more robust in dynamic situations, especially in fast charging. And this is what we want to explore in this presentation a little bit closer. So why do we say it is an addition? Because if you have a state-of-the-art BMS system, you basically have time-based potentiometry. So you're observing something in the time domain. So if there is a current pulse or a step function in the current, you will be observing a kind of pulse response of the cells, typical pulse response with a little ohmic part, and then there is an impedance curve added to it with all the overpotentials of the diffusions and of the different other chemical effects. And if you have a time-based observation, that means you're looking at discrete points in time of this curve. And current BMS chipsets do not have discretized points in time that are synchronized over the whole system. So that means you have different points in time on the current versus the voltage, and you might have even different points in time on different modules, as there is different module controllers. What do you do with this kind of BMS? Naturally, state of charge and state of health estimation and correction. So that means you have some time, you have a model-based system that will regulate over the order of minutes. It will regulate itself to actually detect what is the internal states of the cells. And it will try to do a charge control and prevent an overcharge by imposing rather strict or sufficiently strict limits onto the charge current settings in order to not run out of the dynamic limitations that such a system has. On the other hand side, if you go to add EIS to this, you can observe much faster points. So you can observe up to 1 kilohertz of excitation signals with our system. And in order to observe 1 kilohertz of signal frequency, we need to measure at a higher frequency, like 2 kilohertz, for example. But you can imagine 2 kilohertz data points with 200 cells in an 800 volt system is probably going to be a lot of data points, especially for a central bus and an MCU system. So what we do is we actually transform those data points directly in the device into the frequency domain. So you're observing something in the frequency domain from that point of view. So what is the measured value? It's not voltage and current. It is still voltage and current at the analog front end, but behind the analog front end where the control sits in the MCU, it is actually phase, angle, and magnitude. And this impedance will give you a resistance part, and it will give you a delay part on which you can judge if a certain current will lead to an over voltage at some point in time or not. What are the applications for this? First of all, the impedance is very strongly depending on the temperature. So it is quite well suited for actually taking the 2 or 3 accurate temperature measurement devices that you have on a module and extrapolating them to, or let's say using them to calibrate the impedance on those cells that are directly measured, and then extrapolating to a temperature measurement on all of the other cells. So you can get a temperature estimation for each cell separately within a matter of seconds. Again, this is much faster than the temperature from a cell that is a little bit away from a temperature sensor. The temperature information would actually travel to the temperature sensor. You can use it for cell anomaly detection. That means if one cell behaves differently than the others, we will show you that in which way it can behave differently. This can be detected, and especially for the topic of charge control, it helps you to get the resistance in order to do exact charge control. It gets you the resistance at any point in time in order to prevent the lithium plating. So how do we do that? We have this tool which basically measures a frequency response, but this frequency response, as we said, is already very dependent on the temperature. It is very dependent on the bias current that you have as a base layer. It is dependent on the state of health, and it is dependent on internal load gradients. So that means it is dependent on the trajectory over the last couple of minutes. What did you do with the cell? Are you just coming out of a fast charging event? Are you just coming out of a highway driving event? Are you coming from a rest period? So it will change the electrochemical cell impedance spectrum quite significantly. Additionally to those dynamic features, you will find that the cell form factor, the cell chemistry, and the cell capacity, actually all three will influence the EIS spectrum also in a significant way. And mind you, I put the cell chemistry here, so I mean the electrode chemistry and the electrolyte, as well as the form factor. So even if you have the same cell chemistry, but you have the same cell chemistry in a different form factor, you will receive a different impedance spectrum. With all of this being said, the most important part about it is the comparability between the cells in the as-is status. So in order to detect a temperature variation, in order to detect an internal cell internal cell defect that is developing, the most important part is to be at one time comparable between all of the cells in your battery pack. And this requires a very accurate synchronization of all those measurements so that you are really in sync with all the measurements. So Philippe, maybe you can give us or step us a little bit through how we actually come from the excitation generation all the way to the impedance value.
Yeah, sure. Hello, everyone. So, yeah, the way we do that, of course, we need to have an excitation signal to impose the current through all the cells. And we measure the voltage variation across every cell to see how every cell reacts to this current. So in order to have this impedance measurement, we need to measure at the same time the voltage and the current, and then we so every ASIC does that. So all the BCC, so the BMA 7418, they do the cell voltage measurement. There's one single ADC per channel, and then we have a Fourier transform DFT block that does the, let's say, time domain to frequency domain analysis, and then from that measurement comes let's say complex value of the voltage that integrates both the amplitude and the phase for each cell, and of course the same thing for the current. And then on the MCU side, what we do is we just do the division of the voltage by the current, and then you get the impedance for every cell. So you've got a magnitude value and a phase value for every cell for the impedance. And this can only happen, and maybe you can go to the next slide, because these DFT, it's really important to understand that we need to have a very good synchronization mechanism, because the way the DFT works is it integrates a series of measurement over time, right? And it computes the amplitude and the phase of the signal, like I said before. So this takes a certain amount of time that you can choose as a user to do your DFT over, let's say, 1 second or a fraction of a second, but it takes a certain amount of time, right? Because you need a certain amount of samples to do that. And so to have an accurate measurement for the impedance, because you have this two different entities that you measure, the voltage and the current. So it's crucial that all these measurements that will be happening during the DFT sequence, like 1 second, that they all happen exactly at the same time. If you have some phase variation of when these measurements occur, you will have eventually an impact, let's say a degradation of the accuracy of your impedance measurement, and mostly on the phase. And why is the phase important? When you do an impedance measurement, the phase is very useful, for example, to extract information at the high frequency domain, and especially like the temperature. And temperature, you know, will be very essential to first get the information of the temperature, this is one thing, but also to eliminate the temperature, let's say, information in your model, because if you want to look for state of health, it depends a lot, the impedance over, with the temperature. So you need to eliminate at some point in time the temperature information. So this is why it's very important to have a good phase information of your impedance. And when doing a module level excitation, you can measure both the cell voltage and the current at the same on the same IC. So it's fairly easy to do a good synchronization. But when we do a pack level, which is what we also propose in our chipset, so you only have one current measurement. And so all the voltage measurement need to be perfectly synchronized with this current measurement, right? So the way we've done that and the way we have solved that, we have implemented a synchronization mechanism between all the AFEs, including the current, in the communication daisy chain. We call that the frequency lock loop, or FLL. And the gateway that you can see here, the BMA 6402, can be configured to send a synchronization signal like every 1 millisecond to all the AFEs, and so that they are perfectly aligned to the crystal that is attached to the gateway. In this case, you do synchronization measurement. So the good thing is that the MCU only has to set up a few registers in the IC, and then it's really running independently. So we are completely offloading the microcontroller from this task. So maybe you can jump to the next slide, because here it's an experiment where we have put 13 analog front-end ICs, or BCC in this case, in a chain, and we have actually every BCC is configured to measure one sample every 1.024 millisecond exactly, and every time it does a measurement, it toggles a signal that we can measure, and we can see basically the period of time between every BCC if there's any difference. So as you can see on this graph here, before we run the FLL, every IC is pretty much at its own pace, based on its own oscillator that is not so accurate. So you can see that the period can vary quite a bit around the expected value of 1.024 millisecond. But at some point in time, we actually activate the FLL. This is where we have this red arrow that says FLL running. So at this point, we activate the FLL mechanism. So within a few clock cycles, all the clocks of all the AFEs are perfectly synchronized, and you can see that they are all aligned to the target value, which is 1.024 millisecond in this case. So and after some time, we have this experiment. We have disabled it, and what you can see is that every AFE that's on the zoom on the right hand side diagram, where you can see that they all hang in where they were more or less. So it's less tight, but they kind of stay more or less at the same let's say clock synchronization that they had. So unless you change the temperature, they will stay more or less there. But if you don't do that and the temperature changes, then you will start drifting away, because it's an oscillator-based clock signal that we have in the ICs. So what is really remarkable, and this is what I show at the bottom here, is the performance of this FLL, because we have 150 nanoseconds of standard deviation. So this is how accurate every period is in this experiment over those 13 nodes that we had in the system. So 13 nodes, if it's a 18-channel device, that's a lot of channels, right? A lot of cells. So it's quite a good performance. So that can lead us to actually have a very good accuracy on the EIS measurement.
Yeah. So what is an EIS measurement on a pack level, or how does that look like? Now, let's imagine we have a pack here with 96 cells. So you have a kind of standard automotive shape, and you have 4 big yeah, let's say multi-module controller units. So we have in total here 4 modules, and for each cell we can measure an EIS system, an EIS frequency spectrum. So we would get a lot of points alongside those green curves here. And we actually don't measure here in the solid diffusion range because it just will take too long if you measure in the millihertz region. So a normal time-based BMS system, anyways, can control in this Warburg strait, as it is called in the EIS world. But here in the section around 1 hertz, 0.5 to 4 hertz neck frequency, then up here in the region around 50 to 500 hertz, and in the region at around 1 kilohertz, the really interesting things happen, because with those 3 measurements you can build a triangle, and with this triangle you can actually show the differences that this spectrum, this semicircle, will describe over variations of the cells. So let us start with 20 degrees and 50% SOC. If now the pack is being used and there is some heat influx coming, I don't know, from bus bars and from junction boxes, or the cooling system is not exactly equal, then you will get warmer cells that will have a different kind of spectrum here. And you can see it's still a semicircle, but it is actually moved towards the the high frequency part here, and the same frequency points on the semicircle will actually form a kind of, yeah, let's say straight or at least a kind of linear distribution alongside which you can very nicely find out that this is a temperature gradient. Yeah? If your triangles are basically moved inwards like this. So in this case, you do not need to record all of the frequencies alongside the semicircle in order to try to compare the semicircles with each other, but actually 3 points are quite nice, and you can then do a distribution on each of the frequencies in order to see if the cells have this gradient behavior. So what else can this semicircle show us? If you follow through the literature a little bit, then you find a publication like this here, or you find multiple publications, but we selected one here that actually has a very nice graphics. And you can see that in the case of an internal short circuit, so this ISC here is called internal short circuit, the whole semicircle is shifting or let's say turning towards the counterclockwise, and it is shifting slightly into the 0 direction, so to slightly lower real parts. And this shifting of the semicircle can be described with the shifting of the triangle. So if you have your 3 points and you have another 3 points and you shift the semicircle, you can shift this over. And the second part here is the so-called plating. So this is not yet really a big internal short circuit, but a metallizing of the surface. And you can see that the resistance part of the low frequency EIS is actually going down. So this is basically also the movement in this direction. And if you then look at these publications, you find that most of the publications are actually describing this kind of tilt shift behavior. So a combined turning and shifting of the semicircle. So can we find that in our system again? So again, let's assume you have a cell and you have one cell that really has an internal short circuit. So we named this here cell number 8, and we measured our EIS of all the other cells, assuming that they are at the same state of charge and approximately the same temperature. They should be giving us a distribution like this here. Then cell number 8 would actually give us an outlier on all 3 of those frequencies. Now, what can we do in order to detect such an outlier? We can compare the cell number 8 EIS spectrum to a similar cell in a similar position with a similar influence from the thermal system, with a similar influence from ambient thermal, with a similar influence from plate capacities, from mass, and so on. So a good comparison for this cell here would be the cell number 16 or the cell number 89 or 61 here. Or 81 here. So those three cells would be the neighboring cells basically that have a similar environment as this cell. And then you can compare in the statistics again in the impedance graph with this cell. But for that, in order to compare from this cell to this cell to this cell and to this cell, you want those cells to really be aligned in their excitation and in their frequency response. Because if you have module level EIS and then you have slight differences in the frequency and in the phase angle, you are getting to a distribution that is actually not allowing you, or maybe not allowing you to find such outliers. But maybe Philippe, you can give us again a short description of what we see down here with this distribution.
Yeah, this distribution, if you repeat a measurement on a cell in exactly the same conditions, you will get a certain ability of the ES chipset to reproduce the same measurement over and over. And of course, you want it to be as narrow as possible. So we have worked really a lot to be able to provide a very accurate measurement. And in this case, if you can see here, you have like a 500 micro ohm measurement of the magnitude of the impedance that you expect, and your standard deviation of the measurement is 0.5 micro ohm. So you see it's very narrow. You have a very good, let's say, trust of that what you measure is what is actually the the repeatable. So that's this in this test we repeated the measurement 50,000 times. And here you have a setup that allows us to exercise our chipset. And we have used a module. In this case, it's an NMC module, a 12 cell. Of course, we could stack more up, but in this case, we're just using one CMU that is connected to this module. And we have a shunt that we see a little bit on the side that is measuring the current, and an excitation setup that in this case, it's a passive excitation where we're just toggling on and off a resistor that is loading the battery pack and providing the excitation current. Of course, we have the BMU where you have the gateway and the microcontroller to configure all the AFEs and collect all the data, and then connect, send all the information to a computer. On the next slide, you can see some of the effect that we have when we do a measurement. In this case, I've shown the example of two blade cells that are pretty long, where this effect that I'm going to talk about is the wire influence. So the wire harness can have an influence on the measurement when you do impedance measurement. And why is that? Is because if you can see, let's say you have those two cells that are connected in series, and you have your chipset on one side to do the cell measurement, but you have your excitation source, and that's providing a current flow that is going from one cell, from cell 2 in this case, and then all the way to cell 1, and then returning to the excitation source. So you have this current loop basically that generates some magnetic field, right? And at the same time, you have a sense line that is common for in between the two cells. You need to have this long cable to go from one end to the other end. Of course, there's other arrangement that you can do, but this is a very common arrangement. So in this example, one cell is connected, or this bus bar that you have between cell 1 and 2, you see this red line that is connecting all the way to the BMS for the sense line. And this is also what is used in a traditional pack to do the DC measurements. But now we want to use the same wire harness, because you don't want to use different wire harness for your EIS measurement, right? So you need to just take whatever you have. So in this case, you can see that there's some coupling effect happening. So in the case where the cable, this is position 1, where this sense line is right in the middle. So we do have some coupling because there's some current flowing in one direction, and my sense line is like a transformer, basically, with one spiral, right? Where you actually, as the frequency increases, the coupling will increase, right? So in this case, you are more or less, the first thing I would like to show here is on this diagram that you have on the bottom. This is the Nyquist plot for those two cells with this sense position line. So the first thing that we can notice is that the slight shift on the horizontal axis, so that's the real axis. So you might think, yeah, this is more like a resistive effect, and yeah, true. As the way we've connected it, it was slightly more, let's say, adding a little more resistance because of the bus bar. Just because the sense line you see is more on the top than on the bottom, right? Then it was just adding a little bit of resistance to cell 1. This is exactly what you see. So just a tiny position difference can already lead to some EIS difference. This is how sensitive your EIS measurement is, right? Which is good because you can see so many things, right? So the next thing that you can see also is a slightly phase shift. As the frequency gets higher, you see there's this curve that is more bended for cell 1 to the bottom than the other one, meaning that there's more phase on the cell 1 than cell 2. And so that means that the coupling is slightly different, but it's not too bad, I would say. Now, let's look at the next step, where we change this position line for the sense line and we go more on the top of the cell 2. In this case, you see there's a major impact on the phase at high frequency, where we actually exacerbate some of the phase difference that we had before, but we made it even more important. And you see that the real shift is still about the same, at least for the low frequency region. Okay, so that means that we have more, let's say, coupling with the current in this direction than we have on the other one, because on the returning current, we have more distance. So we are, let's say, having more coupling towards cell number 2 for the positive, and then negative for the cell number 1, right? Because remember, we still use the same cell terminal. So if we add some voltage on this line, we're adding to one cell and we're subtracting to the other cell. So when it comes to the phase domain, same thing happens. And the more you go in frequency or to higher frequency, the more pronounced this effect is. And so it's just physics. It's nothing has to do with the way we measure. It's just the sense position, and this is physics that's happening. So now if we move it to the third position, which is placing it at, on top of cell 1, you'll see that the effect is just the opposite. And we'll just, so bottom line, what I want to say here is that there is some wire harness coupling that may affect your measurements. So there's some things that you can do. You can improve your wire harness if you have this flexibility to place your sense line at different positions. You can do so that you can minimize, but you can also do a numerical, because this depends on the position. So if your wire harness is at a fixed position, you can correct this numerically, and then from the unoptimized and non-corrected measurement to the optimized and digitally corrected waveform. Then they are all superposed, and you can use your algorithm based on this correction, basically.
So this is probably something that you would want to do directly in the development of such a system as part of the calibration and adaptation of the system to your design. So what can you do with this now? What is it, and how can you charge actually faster, or why can you charge faster when you have EIS? Let's look at a real-world example with an 800-volt fast charging cycle of an SUV that's in the market already. So we have used a profile that is available from the market, and you can see that this car actually comes to the charging station with about 20 degrees on the minimum, 23 degrees maximum. So it's quite empty with 9% SOC. So it's ready for a good and thorough fast charging. Now, what happens is that the vehicle actually increases the current, not to the full extent, but about 2/3 of the way. And then there is something visible here that I would say is a kind of idea to try to go up and down with the current a little bit in order to provoke the battery cells to have a certain voltage pulse or current pulse to induce a voltage jump. That is kind of a resistance probing. So you could say it's a kind of low frequency pulse impedance spectroscopy that is happening here in order to find out what the actual resistance of the cells is and how far could you increase the current before you actually run into an overvoltage situation. So after a certain amount of time, charge is going on, you can see the cooling system is running, battery temperature is increasing. The BMS actually decides to jump to a higher charge current, increasing this pulse frequency higher than there is some dedicated pulses only downwards anymore in order not to create current voltage spikes upwards. Then there is a kind of very flat period, and then here for some reason the temperature actually goes a little bit up to about 40 degrees, but the cooling system is actually shutting down. So maybe due to the risk of plating, the cooling system is not running too harshly at that time, where you have the cell being warm on the top side, cooled down on the bottom side, but it's already at a significant SOC here. So there is probably a risk of actually creating plating on the bottom side of the cell, on the cold side of the cell. So the cooling system is shutting down, the temperature is rising quite significantly, and the current is actually reduced in order to cope with the temperature increase that is happening here. And then at the lower current, the game starts again. The cooling system sets back in actually and runs again at a slightly higher temperature than before. Not 20 degrees or 23 degrees anymore, but rather 25 degrees. And there is a stepwise reduction in current until a point in time where the maximum temperature here is 48 degrees or 50 degrees, and there you see that it goes into a kind of CV mode. So there is 3 to 4 different kinds of operating strategies within one fast charging cycle. And just mind you, this is just 17 minutes. So temperature sensors that show us this curve increase here, they really are at the borderline of their capability to actually sense the changes fast enough that are happening due to simple diffusion of temperature speed. So when you think of optimizing this procedure here, then the first part is to optimize here. How can we get to a higher charge current, and how can we get to resistance measurement faster at this point in order to cover a higher charge current here? And how can we then detect the risk of plating at a certain given coolant temperature in order to stay at a higher current for a longer amount of time? Now, this is exactly what EIS is supposed to do. The BMS checks the temperature sensors. The BMS initiates, as we said, the 3-frequency measurement, and the BMS can compare the per cell EIS results with the temperature sensors for consistency, and then it creates a temperature distribution within a second for the whole module. So you would see if there is any kind of higher temperatures or cells, single cells that have a higher temperature in the module. If the EIS spectrum by itself is consistent between the cells, as we said, there is no outliers, there is no detection of any kind of statistical deviations, and the hottest and coolest cells are identified. If this is not good, raise a cell safety issue, reduce current. But if it's okay, and let's say most of the time it should be, at least if you have a quality battery system, then you can use those values actually to define the new maximum current. And you can use the lowest temperature cell, highest SOC cell for the maximum charge current definition. And you can negotiate with the charger to go to the right current setting. So what does that look like then in the diagram or in a similar diagram? Basically, we do an EIS at the starting point in order to establish a baseline. Then the current is increased. Measurement is continued. So mind you, measurement takes a couple seconds in order to equalize out the noise with sufficient measurement points. So we're in the order of 30 seconds here with our second and third measurement point, reaching a full speed charge because we have established a good understanding of the resistance of the cells, even in the highly nonlinear part with high current charge. And then we can steer the pack into a decision or into a current situation in which it does a nice high CV curve, and it can detect cells that are plating on the bottom side, on the cooling side, with high frequency 1 kilohertz EIS. So 1 kilohertz EIS is used in production facilities today in order to understand if cells have internal short circuits or if they have plating after formation. And this same 1 kilohertz measurement is now available for you in the field in order to check exactly the same thing. If you're cooling the cell, if you're undercooling the cell on the bottom, and creating a possibility for a plating in that area near the cooling system. And then you come to safely reach the maximum charge of the cells, hopefully at a faster speed than before. So how do you change to that system, and how can you get that system integrated into your BMS system? We have our devices here with the chipset that is available until now, so the 7118 and the 777 for the BJB and the Gateway 665. And these can measure voltage and temperature in the BCC and current in the BJB. There is a complex device driver software development kit available for this state-of-the-art BMS system. And you can now go for pin-to-pin compatible replacement with the new devices. Mind you, a 4 in the second position of the number indicates the capability to go for EIS, which means you get an impedance measurement additionally. And then there is the pre-charge control device, the TAA 3033, that can be attached to the BJB device in order to do the excitation control. All of these devices are fitting to our newest version of the complex device driver software kit that we are publishing on our website, and that you can download from the website in order to generate new control algorithms that are using impedance as the control parameter. With that, I want to leave you with a short summary of the features that we have talked about. So if we map them back basically onto the different applications, we are trying to improve fast charging speed by inline temperature and resistance monitoring. We are supporting this improvement of safety of the battery by understanding what the trigger events could be, and monitoring for trigger events even very long time before any kind of event is happening. So we have done some testing on this, and we were able to see hours before a thermal event actually a change in the EIS signature. We have a consistent monitoring for internal short circuit that is very similar to what you do in the warranty control or in the warranty handover between a tier 1 and an OEM today with a 1 kilohertz EIS pulse. And then you can also improve your SOX buffers by doing a very fast cell-to-cell compare, improving your balancing algorithms based on the resistance measurement that you have, and also the resistance measurement leads to a robust state of function or state of power, depending on the nomenclature that you use. So I hope I got you interested in trying the value of an EIS-enabled chipset, and I think we're opening for questions.
Yes, indeed, we are opening for questions now. Thank you so much, Wenzel. That was a great presentation. And I should also mention Philippe. Philippe wasn't able to join us live today to take your questions, but Philippe is a BMS applications manager at NXP Semiconductors. So, Wenzel, how did you become so familiar with all of this over time? How many times have you done this presentation?
Oh, it must be quite a bit of times. The first time I actually dealt with EIS was in 2009 on single cell EIS development, on testbed development for EIS, and then we built some EIS systems into cars as part of European development projects in 2014, 2015. So it has been quite a bit of exposure there, and that's why probably there is a little bit of a longer answer.
I can certainly tell you know what you're doing. That's why I said in the beginning there would be no one better to tell us about this. We are taking questions. We have about 200 people watching across various platforms. So please drop your questions in the chat wherever you are, LinkedIn, YouTube, Facebook, StreamYard. Let's go for the first question here from Rahul. He wants to know, what are the options for excitation that have been tested in NXP solutions?
So we have tested multiple different options for excitation. We started with very simple excitation options where we just actually burned energy basically in a switch on, switch off against a resistor. We also tested the pre-charge based solutions where we used the active pre-charge device in order to shuffle energy between the cells and the DC link capacities of the high voltage devices that are linked in the system. We also tested some of the excitation solutions with customers that are using directly the incoming stages of the inverters. So basically, you use the same energy storage, secondary energy storage, being the DC link capacity, but you're limiting yourself to the one in the inverter, and you're using the inverter incoming stage directly as the controlling device. And we're also developing with a partner together a solution towards a half-pack excitation. So basically, to take two halves of the pack and have DC-DC or have a kind of a switching of energy between the upper and the lower half, if you want, of a battery pack.
Great. Question from Adrian J, who wants to know, how accurate are impedance measurements during a typical drive cycle with varying drive current?
So the thing about impedance measurements, if you're using them during a drive cycle, is that you want to do relative measurements. You want to measure a cell to another cell. And during the drive cycles, this definitely depends on the dynamics itself of the drive cycle. You can finish an EIS segment of 3-4 frequencies in about 15 to 20 seconds. So if you're sitting at the light for half a minute, you could actually do an EIS there as well. Other than that, as long as you are measuring all the cells at the same time, you're actually getting all of the disturbances of the drive cycle into each of the cells. So again, the cell-to-cell comparison is okay. Please do not try to compare results that you do or measurements that you do during a drive cycle to an absolute value or to a time-based or SOH-based value for impedance.
Okay, sitting at the light. Times have changed. Peter wants to know if the chipset is applicable for monitoring hydrogen fuel cells and electrolyzers.
So the chipset is made for battery management systems. That means the typical voltage ranges of the battery management are also needed. If you want to use different devices that have a lower voltage per cell, then there is multiple things that are let's say, different. Under which the most important is that the chipset is built for supplying itself out of the battery cells. So that means during the operation, the power for the device comes directly from the battery cells. And that means the fuel cells would have to be running all the time, or you have to put external power supplies to the devices. So they're not purpose-built for hydrogen fuel cells and electrolyzers, unfortunately, for Peter.
Sorry, Peter. We'll get there. I just want to ask something. If I can look down at your slides that you showed earlier, you showed some graphs with green traces where you had unoptimized, and then you had optimized layout and digitally corrected. So when you say digitally corrected, what are you correcting for in the model? Is harness inductance or trace resistance or
Yes.
contact resistance? What are you correcting for?
So when you have a wire harness on a battery module, then you basically are creating different sized antenna loops towards the different cells, because one cell is farther away from the module controller than another cell. So you have to create a bigger antenna loop to actually measure that cell. And since their cells are connected in series, most of the times they are kind of AB stacked. So one flat, one the other way around. And that means the current is actually flowing through those antenna loops in the opposite direction every second cell, or every other cell, the same direction and in between the opposite direction. So we're correcting for those factors, that the current is flowing through the antenna loops.
Amazing. Question from Jens here. Do you have a collaboration with the university for further research on EIS, or is it all in-house research and development?
No, we do have multiple collaborations with universities and research centers. So there is universities in Germany, Italy, Denmark, Netherlands, China that we are working with.
Awesome. We're coming up on the top of the hour soon, but I'll take a question from Hans-Jörg Böhmer. Is your chipset capable? Sorry, he asked two questions. Let me get to his first question. Is your chipset capable of providing predictive maintenance?
So predictive maintenance is so the answer is yes and no, depending on what you exactly find under predictive maintenance. And Hunter, please feel free to specify that. We are able to provide the values to support predictive maintenance models with our safety measures and with our let's say maintenance measurements that we have on the chipset. We do not have those directly implemented in our drivers or in the silicon. So that's why it's yes and no.
Okay. He did mention actively preventing solid electrolyte interface. That was his second comment.
Didn't scroll down far enough. So yeah, when you have a solid electrolyte phase cell, then your main problem is actually that you have internal short circuits growing along the phase boundaries, the grain boundaries of the solid electrolyte towards the other side. And those actually do behave very much like the internal short circuits in liquid electrolyte cells. So yes, you can see them in the EIS. Unfortunately, what I'm saying here is not tested by us because we don't have too many solid electrolyte cells that are, let's say, high maturity or better maturity than lab and research grade. But at least you can read it from literature, you can read it from multiple measurements that there is the possibility to detect the internal short circuits in solid electrolyte cells with EIS.
Okay. Wenzel, we have gone over the hour, but I've got a couple more questions. Can you hang around for a couple minutes for a couple more?
Yeah, let's take the one from Raul for a moment.
Sure. You said that there is software available. When and where?
So the software is available as soon as we do our full market launch. It will be available on the NXP homepage. So you can go there and watch the device. As soon as it comes from pre-production to production setup, you will find the link to the software. Other than that, if you have a direct connection to NXP with an NXP account and a secure account, you can contact me or any of the NXP representatives to be able to talk in more detail about this.
Well, great. Thank you very much for that and for all your answers. And thank you to everyone who joined us from around the world. I saw, once again, Colorado to the Philippines. So the whole world was watching. And thank you to Wenzel Prochazka for joining us and giving us this illuminating presentation, which clearly was very well rehearsed and very insightful. So thank you, Wenzel, for joining us.
Thank you very much for having us here and for listening.
Absolutely, and thank you for your support, and thanks for bringing us this show from NXP. To everyone around the world watching, thank you again for joining us, and stay tuned at electromagazine.com, where we can tell you about more webinars that are coming up in the future. To the world, good morning, good evening, good afternoon, wherever you are.